Good afternoon, everyone. How are you guys doing this afternoon? I'm glad to hear that you guys are doing well. How did your calculus test go last night? Not too bad. That's good to hear. So, we're going to continue today with our discussion on galaxies and also our family of galaxies. So, I thought I'm going to decide to show you two quick videos on galaxies before.
We live in a pretty cool neighborhood, the Milky Way galaxy. We're out in the suburbs, sure, but it's still an interesting place, buzzing with activity. Stars, nebulae, stellar clusters of various sorts, the occasional supernova. It's a happening place. In the earliest part of the 20th century, astronomers were just starting to figure this all out. But there were a handful of objects that were puzzling. Dotting the sky here and there were faint fuzzies displaying a variety of shapes. Some were round, some elongated, and some even seemed to have spiral arms. Even with big telescopes, they looked smoky, so they were simply called nebulae. Their existence was puzzling, though. What were they? How did they form? Were they big, small, near, far? Eventually, astronomers had uncovered the key to these objects, and in one fell swoop, our universe got a lot bigger. A lot. In 1920, there were two competing ideas about the universe. One was that our Milky Way was it, and that everything we saw was in it. The other was that these spiral nebulae seen in the sky were also like our Milky Way, island universes in their own right. Two astronomers debated this controversy in that year. Harlow Shapley argued that the Milky Way was all there is, while Heber Curtis was of the opinion that we were one of many galaxies. It wasn't a debate as such, more of a presentation of ideas, and there was no clear winner. Both sides had fragmentary data and, we now know, some shaky observational evidence that turned out not to be correct. For example, Shapley noted that one of the spiral nebulae had been seen to rotate, so it must be small. It turns out that was just wrong, dead wrong. On the other hand, Curtis noted that if galaxies were as big as Shapley claimed, hundreds of thousands of light years across, then other galaxies must be impossibly far away. But hello, galaxies really are that big, and they truly are mind-numbingly distant. The observation that finally unlocked this mystery was made just a few years later when Edwin Hubble and Milton Humason observed the Great Spiral Nebula M31 in Andromeda, using what was at the time the largest telescope in the world. They found dozens of pulsating stars in it, literally stars that change their brightness in a regular periodic fashion. These are called Cepheid variables, and they were critically important because it was known that the time it took them to pulse was directly related to their luminosity, how much energy they emitted. That means if you can measure their period, you can determine how far away they are simply by measuring their apparent brightness. The distance they found to M31 was 900,000 light years, clearly outside even the largest estimates of the size of the Milky Way. They also resolved swarms of faint stars, cinching the fact that the Great Andromeda Nebula was actually the Andromeda Galaxy. At that moment, our understanding of the universe swelled in size, and we've never looked back. We've learned a lot about galaxies in the ensuing century or so. Each is a collection of at least hundreds of millions or even trillions of stars, and most contain some amount of gas and dust. They range in size from tens of thousands to hundreds of thousands of light years across, and they come in a variety of shapes. We use these overall shapes to classify them. Broadly speaking, there are four major types of galaxies: elliptical, spiral, peculiar, and irregular. Spiral galaxies we've seen. We live in one. These are characterized by broad, flat, rotating disks of stars, gas, and dust. a central bulge of older, redder stars, sometimes with a long cylindrical or rectangular bar of stars as well, and a huge extended halo of older stars. Some spirals have large central bulges and some have much smaller ones. Most have bars of stars extending across the central part of the galaxy. Our Milky Way does. The spirals come in a variety of flavors as well. Grand design spirals have magnificent, well-organized spiral arms that extend from the very center out to the visible edge of the galaxy. Others have choppy or patchy arms. These are called flocculent spirals, resembling tufts of cotton. Some spirals have wide-flung arms, while others are tightly wound. Spirals take on wildly different appearances depending on their angle to us. Some we see face-on, and these may be the most magnificent objects in the entire sky. Huge and sprawling, their structure is obvious and easy to see. Star-forming nebulae are laid out like beads on a string, colored pink by the characteristic glow of warm hydrogen. Young, massive, luminous stars blaze blue, tracing the spiral's form. Filigrees of dust clouds align with the arms as well, and the central bulge or bar glows an eerie reddish yellow. The star formation there long since ceased. The bluer stars all exploded, leaving only the redder stars behind. When spirals are more tilted to our line of sight, some of this structure is hidden. And when they're edge-on, we see them as the flat disks they truly are. Dust clouds are tightly restricted to the midplanes of spiral galaxies, and we sometimes see them bisecting the galaxy like a racing stripe right down the middle. The reason for this is the same reason our solar system is flat. Galaxies probably formed from huge clouds of gas billions of years ago. As a cloud collapses, small eddies in the gas would get amplified and would create an overall spin. This naturally leads to a flattening of the cloud, and by the time the stars in the galaxy were starting to turn on, the overall structure of a flat disk was in place. Elliptical galaxies are, well, elliptical. Kinda. Some are nearly spherical, gigantic cotton balls of billions of stars. Others are more elongated, shaped like cigars or American footballs. They tend to have no overall structure as spirals do. Ellipticals are puffy, and they range in size dramatically. Some are what are called dwarf ellipticals, just a few thousand light years across, to monsters that hugely outmuscle our own Milky Way. Besides their shape, ellipticals are characterized by a lack of gas and dust in them, and also are populated with older stars. Apparently, star formation in ellipticals came and went eons ago, and all the young massive stars have long since exploded, leaving less massive redder stars. This makes them similar to the stars in the central bulges of spiral galaxies. It's not exactly clear how ellipticals form. Current thinking is that they are the products of, and this is mind-blowing, galactic collisions. Yes, you heard me, entire galaxies collide. When galaxies collide, it's a train wreck on a cosmic scale. Galaxies are huge structures, and with hundreds of billions of stars in them, their gravity is pretty strong. If two galaxies get close enough together, they can draw each other in and collide. A galactic collision is a weird event. Even though the collision speeds can be hundreds of kilometers per second, the event plays out over hundreds of millions of years. Remember, we're talking about distances of tens of thousands of light years here. In the early stages of the collision, tidal effects can be strong. Stars on the side of the galaxy near the other one get pulled toward it more strongly than the stars farther away, so the galaxies can get stretched and long tendrils of stars and gas get drawn out. Generally, collisions aren't head-on, but more of a side swipe, so there's some sideways motion. When that happens, the tidal streamer can become curved, a long, graceful arc. Colliding galaxies in this stage form all sorts of bizarre and spectacular shapes. Sometimes the galaxies separate and then fall back together again. When that happens, the main bodies collide. But this isn't like two cars crashing together. Stars are very, very small compared to the space between them. So even though hundreds of billions of stars can be involved, the odds are good that no two stars will ever physically hit each other. Space is weird. Gas clouds, though, are huge, and they do collide. They slam into each other, collapse, and form stars at a furious rate. Colliding galaxies can glow pink and blue as stars are born and light up the hydrogen clouds around them. Sometimes the two galaxies will collide at high enough velocity that they pass right through each other. But even then, in most cases, they'll slow, stop, and then recollide. Eventually, they merge, their huge energies of motion absorbed by the orbiting stars, puffing them up into vast, sweeping orbits. The results, so we think, are elliptical galaxies. Not all collisions result in galaxies becoming ellipticals. If a big spiral collides with a much smaller galaxy, it can tear apart the interloper and literally absorb it into itself. So, galaxies are cannibals. We think most large galaxies grew to their current bulk by consuming smaller galaxies, including our own Milky Way. In fact, we have proof. We're currently in the process of eating several smaller galaxies right now. Tirzan 5 is a small knot of stars that may be the leftover core of a galaxy cannibalized by our own. And two huge looping streams of stars circling our galaxy are parts of the Sagittarius and Canis Majoris dwarf galaxies being torn apart by the Milky Way. This brings us to the third type of galaxies, peculiars. These are not shapeless really, but have a shape that's weird. Peculiar galaxies are essentially all due to collisions. Colliding galaxies clearly have structure, but can be all sorts of odd, distorted shapes. Sometimes a small galaxy will plunge right through the heart of a much larger galaxy. The gravity of the smaller galaxy draws in stars and then flings them away in the bigger one, like ripples in a pond. The result is a ring galaxy, sometimes with the culprit intruder seen nearby. The famous Cartwheel galaxy is a fine example of this. Another is Hoag's object. Though, to be honest, it's not completely clear if this bizarre galaxy is a product of a collision or some other process. It's peculiar either way. Finally, we come to galaxies that truly are shapeless, called irregular galaxies. These tend to be small and chaotically shaped. Bigger ones may be victims of collisions, their shapes distorted so much that the structure was lost. Smaller ones may simply be too tiny to collect themselves together into a recognizable shape. Many galaxies have companion satellite galaxies. The Milky Way has a couple of dozen such satellites. The two biggest are the Large and Small Magellanic Clouds, visible from the southern hemisphere. Both are irregular in shape, though the Large Magellanic Cloud is barely coherent enough to qualify as a disrupted, though small, barred spiral. Both are riddled with gas and dust. The Large Cloud sports the biggest and most active star-forming gas cloud in any nearby galaxy, the Tarantula Nebula. It's producing so many stars that astronomers think it may be in the process of forming a globular cluster. There are other types of galaxies as well. Some, called active galaxies, pour out far more energy than normal ones. And galaxies aren't just scattered evenly across space. They tend to be found in clusters, some containing thousands of galaxies. We'll get to all that in the next episode. The universe is far, far larger than just our Milky Way galaxy. It's a recurring theme, isn't it? We thought the Earth was the center of creation, and then the sun, and then the galaxy. But every time we investigate these situations earnestly and engage in honest debate, we find that we're smaller and farther removed from the action than we thought, or than we thought we deserved. Astronomy is really, really good at putting us in our place, but it's also really good at showing us just how grand and awe-inspiring blade here. In our last episode, I talked about galaxies, vast collections of gas, dust, and upwards of hundreds of billions of stars. We live in one, the Milky Way, a gigantic disk galaxy with sprawling spiral arms. Other galaxies are elliptical or irregular or peculiar, but those are classifications based on shape. We also classify galaxies on their behavior, and sometimes even on their location and mass. To understand why, we have to take a step back and look at the environments in which galaxies sometimes find themselves. And if you thought galaxies were big and powerful, well, I'm about to crush your brain again. In the 1960s, a peculiar object was found called 3C273. Through optical telescopes, it looked like an unassuming blue star, but through a radio telescope, it was seen to be ablaze with light, a luminous powerhouse. Stars didn't blast out that much radio radiation, so this was baffling. The mystery deepened when spectra of 3C273 were taken. It wasn't a star, it was an entire galaxy. And not just any galaxy, but one very, very far away, well over 2 billion light years. Far from being some dim thing, 3C273 revealed itself to be the most luminous object in the universe ever seen at that time. It blasts out over 4 trillion times the energy the sun does. And yet it appears star-like, a mere dot in the sky. Because of this, it was dubbed a quasi-stellar radio source, which is pretty underwhelming for the most powerful energy source in the entire cosmos. Happily, the name was shortened to quasar, which, you'll admit, is way cooler. Once 3C273 became known, lots more such objects were found. With the advent of X-ray observatories launched into space, even more energetic point sources were found, which is amazing. X-rays are a very high energy flavor of light, and it takes a lot of power to make them. Eventually, galaxies like these were even found to be blasting out gamma rays, the very highest energy kind of light. Clearly, these were no regular galaxies. Astronomers gave them the generic name active galaxies and classified them into various subcategories depending on how they emitted their light and what kind of spectra they had. But what could power these immensely energetic galaxies? It turns out to create that kind of energy, you need to have an object with a lot of gravity. And what kind of object has a lot of gravity? In the 1980s, astronomers were getting suspicious that all large galaxies had very massive black holes in their cores. In fact, one of the reasons the Hubble Space Telescope was built and launched was to explore this idea and characterize, that is, find out as much as it could about, these black holes. Over time, we've found this idea is absolutely correct. Every big galaxy we see appears to have a huge black hole in its heart. Even the smallest is a monster with millions of times the sun's mass, and some tip the cosmic scale at billions of solar masses. We now think that these supermassive black holes form at the same time galaxies do. As the material coalesces to create a galaxy, some falls to the center and feeds the black hole there. It grows as its host galaxy does. But I can hear you thinking, hey, Phil, don't black holes suck down everything, even light itself? How could they power active galaxies, the brightest objects in the universe? You can't escape from a black hole once you fall all the way in. Just outside the black hole's event horizon, things can still get out. If a black hole is sitting all by its lonesome out in space, it's, well, black. But if matter, like gas, dust, or even whole stars, falls into the black hole, it can be shredded by the fierce gravity. This material forms a flat disk called an accretion disk, the matter swirling madly at ferocious speeds before falling in like water down a bathtub drain. Stuff closer to the black hole orbits faster than stuff farther out. This means material in the disk rubs together and heats up, just like rubbing your hands on a cold day warms them up via friction. But around a black hole, the orbital speeds are near the speed of light. Try rubbing your hands together at a couple of 100,000 kilometers per second and see how much heat you make. So friction and other forces heat the material falling in to millions of degrees, so hot that it blasts out light across the electromagnetic spectrum. And that's what powers active galaxies. The black hole is the energy source, but the matter falling into it is the actual light bulb. Active galaxies are so bright they can be seen clear across the universe. Not only that, but some active galaxies have jets. Magnetic fields coupled with the incredible rotation of the accretion disks can launch twin beams of matter and energy directly away from the black hole along the poles of the disk. These beams pack a huge wallop, traveling for hundreds of thousands of light years. Eventually, they slow down as they ram through the thin material between galaxies. But when they do, they puff up. They look like huge cotton swabs which glow in radio waves. Active galaxies can look pretty different from each other, and we now think that's due to our viewing angle on their accretion disk. When we see it edge on, the thick dust in the disk blocks the intense highest energy light, but we do see lots of infrared, as the radiation from the disk heats up clouds of dust around it. If the accretion disk is tipped a bit to our line of sight, we see more optical and high energy light from it. And if the poles are aimed right at us, all that ridiculously energetic X and gamma ray light can be seen. The Milky Way has a supermassive black hole in its heart too, with a mass of over 4 million times the sun's. That might sound huge, but remember, the galaxy has hundreds of billions of stars in it. The black hole is only a teeny tiny fraction of the total mass of the Milky Way. Our black hole is quiescent, that is, not actively feeding, so we're not an active galaxy. Every now and again, we'll see a flare from it as it swallows down a gas cloud or something like that, but nowhere near what's needed to switch it fully on. Happily, we appear to be safe from any tantrums it might throw, but that may not always be the case. One way to flip such a black hole from milquetoast to monster is through galactic collisions. When two galaxies collide, a lot of gas can be dumped into their centers where it can be gobbled down and heated up. We do see a lot of evidence that active galaxies are disturbed, as if they recently collided. So, could that happen to us? Yes. Yes, it can. In fact, it will. But not for a few billion more years. To understand that, we have to take a small step back. Well, actually a huge step back, a few million light years, and take a look at where galaxies live. Our Milky Way isn't alone. It's part of a small knot of galaxies we call, in long, boring astronomical nomenclature tradition, the local group. It consists of a few dozen galaxies, most of which are small and dim, so faint that we're still discovering them. Two galaxies completely overpower the group: the Milky Way and the Andromeda Galaxy. The local group is elongated, almost dumbbell-shaped, with the Milky Way on one side and Andromeda on the other. In the past, the local group probably had lots more galaxies, but over the eons, the two big galaxies ate them all, growing huge. Andromeda is bigger than we are and has more stars, but honestly, we're both pretty big as galaxies go, and someday we'll be bigger. The Andromeda Galaxy is about 2.5 million light years away, close enough that it can be seen by the naked eye on dark nights, the most distant object easily seen without aid. Spectra taken of Andromeda reveal an interesting fact. It's headed right for us! Its spectrum is blue shifted, meaning it's approaching us, and it's doing so at quite a clip, about 100 kilometers per second. That's fast, but 2.5 million light years is a long way. The collision is inevitable, but it won't happen for several billion years. When it does, both galaxies will stretch out due to galactic tides, forming long, curving streamers of stars. They may pass by each other during the first pass, but over the next few hundred million years, they'll slow, fall back toward each other, and merge. They'll then form one much larger galaxy, probably an elliptical, which astronomers have called Milkomeda. I know that's awful, but if you can come up with a better name, let us know. Anyway, although this won't happen for billions of years, that's still long before the sun dies. The Earth may still be around when the galaxies collide. It's not clear what will happen to us. The sun may continue to lazily orbit the core of the new galaxy, or it may move farther in toward the center or farther out in the galactic suburbs. And here's another fun fact. Andromeda has a gigantic black hole in its core too, which has 40 million solar masses, 10 times the mass of ours. When the galaxies merge, the two monsters will probably go into orbit around one another. Not only that, but any gas and dust left over from star formation during the collision may fall toward the center of Milkomeda, where the two black holes will gobble them down, and may turn the galaxy into an active one. Hopefully, any death rays launched from that will miss Earth, but that won't happen for like 4 billion years anyway. I'm not too concerned over the fate of the Earth at that point. I feel that right now is a good time to give you a heads up. We're about to take a very, very big step. Up to this point in the series, we've talked about some pretty big distances. Millions or billions of kilometers to the planets, trillions of kilometers to the stars, and then jumping to thousands of light years, quadrillions or quintillions of kilometers when talking about the galaxy itself. But those distances are as nothing when you start talking about intergalactic trips. We're about to venture out into the greater universe, and things are about to get very large. When we step outside our Milky Way, we find that a few galaxies have clumped together to form the local group. But as we look farther out into the universe, we see that galaxies tend to clump together on larger scales as well. Many are in small groups like ours, but sometimes they aggregate into much larger galaxy clusters. A typical galaxy cluster is a few tens of millions of light years across and can contain thousands of galaxies. The nearest one to us is the Virgo cluster, located about 50 million light years away in the direction of the constellation Virgo. It has well over 1,000 galaxies in it, maybe twice that much. It may have as many as a quadrillion stars in it. Like star clusters, galaxies and galaxy clusters are bound to the cluster by their own mutual gravity and move through the cluster on long orbits that can take billions of years to complete. Thousands of clusters are known, and they contain every kind of galaxy imaginable. Spirals, ellipticals, irregulars, peculiars, active galaxies. In many clusters, a huge elliptical galaxy sits right at the very center. This is probably the result of collisions between smaller galaxies. When they smack into each other, their velocities through the cluster tend to cancel out, like two cars hitting head-on and stopping, so they fall to the center. As more mass falls to the center, the galaxy there grows huge. As mind-boggling as this all is, we're not done. Surveys of the sky have revealed that not only do galaxies clump together in clusters, but clusters themselves fall into even bigger groups called superclusters. A supercluster usually has several dozen clusters making it up, and are hundreds of millions of light years across. Our local group is near the Virgo cluster, and both are part of the Virgo supercluster. Recent observations indicate the Virgo supercluster is actually only an appendage of the even larger Laniakea supercluster, which may have 100,000 galaxies in it, stretching across 500 million light years. This new result is a bit controversial. I mean, it's hard to know exactly how big such a structure is, especially when we're inside it. but it gives you an idea of the vast sizes and distances we're talking about here. Superclusters themselves aren't just randomly distributed through the universe either. They appear to fall along tremendously long, interconnected, and intersecting filaments, making the universe appear almost foamy on the biggest scales, like a sponge. In between the filaments are vast regions relatively empty of galaxies called voids. This cosmic large-scale structure, its size, shape, distribution of matter, and more, holds clues to some of the biggest questions we can ask. What is the universe made of? How did it start? What is its eventual fate? These are questions we'll get to in future episodes very soon, and I promise you they'll stretch your mind like nothing you've ever encountered before. But before we wrap up, there's one more thing I want you to see. When you look at all these pictures of galaxies, of clusters, of superclusters, a question pops up. How many galaxies are there? Can we count them all? To help answer that question, back in the 1990s, astronomers used the Hubble Space Telescope. They pointed it toward the emptiest part of the sky they could, a spot with little or no stars, nebulae, or galaxies in it. They then let it stare, simply collecting light from whatever it could see, letting light accumulate until incredibly faint objects could be detected. And what did it find? Wonder. Pure, simple wonder. Oh yeah, and thousands of galaxies. This is the Hubble Deep Field. Mind you, the area of sky you see here is roughly the same as the apparent size of a grain of sand held in your palm with your arm outstretched. And yet, in that tiny section of sky, there are thousands of galaxies. Essentially, everything you see in that image is a galaxy, a huge collection of gas, dust, and billions of stars. The deep field was repeated in different parts of the sky, and the result was always the same. Crowds of galaxies jostling for position, crammed together even in a tiny slice of the heavens. You can count all the galaxies in these deep fields and then use them to extrapolate the sky, giving you the total number of galaxies in the universe. And what do you get? Well, give or take, 100 billion galaxies. 100 billion. And each with billions of stars. The universe is mind-crushingly huge. And yet, here we are, a part of it, learning more about it all the time. It's easy to think the universe is too big to comprehend and makes us seem tiny and insignificant in comparison. To me, the opposite is true. It's our curiosity about this enormous cosmos that makes us significant. We yearn to learn more, to seek out knowledge. That doesn't make us small. It makes us vast.
So hopefully that provides us with a bit of an overview of what we are going to learn about in this lecture. Do you guys have any questions so far? Okay, so let's begin. So we need to put together our family of galaxies. So for this, we need to understand the shapes of galaxies. So astronomers classify galaxies according to their shapes in photographs made at visual wavelengths using a system developed by Edwin Hubble in the 1920s. And such systems of classification are a fundamental technique in science. So firstly, many galaxies have no disk, no spiral arms, and almost no gas and dust. In these elliptical galaxies, so we abbreviate it as class E, E for elliptical, range from huge giants to small dwarfs. Then secondly, disk-shaped galaxies usually have spiral arms and contain gas and dust. And some of these spiral galaxies, so we abbreviate it with S, so therefore class S, have a central region shaped like an elongated bar and are called barred spiral galaxies. So if it's barred, it's SB. So you learn in chapter 12 that a Milky Way galaxy is a barred spiral. A few disk galaxies contain relatively little gas and dust, and these are called lenticular galaxies. So they are a S0. The 0 is for little gas and dust. Finally, notice that irregular galaxies, I for irregular, so therefore class I, which are generally shapeless and tend to be rich in gas and dust. So for the test in the, or rather for the exam, know these classifications. Know what a class E is, S is, SB is, S0 is, and I is. It is surprisingly difficult to figure out what proportions of galaxies are elliptical, spiral, or irregular. In catalogs of galaxies, about 70% are spiral, but that is misleading because spiral galaxies contain hot luminous stars and clouds of ionized gas that make them easy to notice. Most ellipticals are fainter and harder to notice. Small galaxies such as dwarf ellipticals and dwarf irregulars are actually very common, but they are hard to detect. From careful statistical studies, astronomers estimate that ellipticals are actually more common than spirals, and that irregulars make up about 25% of all galaxies. So how many galaxies are there? So long exposure images of the small areas of the sky are called deep fields because they detect the most distant galaxies in deep space. So this is the famous Hubble Deep Field image that I talked about in yesterday's class as well. But one thing is, in radio telescopes, you can also take deep field images of the sky, and then you can get other data from those galaxies in different wavelengths as well. So what are the properties of galaxies? What are their diameters, luminosities, and masses? Just as you study of stellar characteristics in chapter 8, the first step in your study of galaxies is to find out how far away they are. Once you know a galaxy's distance, its size and luminosity are relatively easy to find. Later in the section, you will see that just as for stars, finding the masses of galaxies is more difficult. The distances to galaxies are so large that it's not convenient to measure them in light years, parsecs or kiloparsecs. Instead, astronomers use the unit megaparsec or 1 million parsecs. So for the exam, I could ask you to define what is a megaparsec. So 1 megaparsec equals 3.3 million light years, or approximately 3 times 10 to the power 19 kilometers. So here in this image, we can see a distribution of galaxies. So in the y-axis and in the x-axis, and how many megaparsecs they are away from one another. So to find a distance to a galaxy, astronomers must search among its stars, nebulae, and star clusters for familiar objects whose luminosity they know. Such objects are called distance indicators because they can be used to find a distance to a galaxy. Astronomers refer to them as standard candles, and if you can find a standard candle in a galaxy, you can judge its distance. And we've done almost the same thing with stars as well. Shaped variable stars are a reliable distance indicator because their period is related to their luminosity. The period luminosity relation has been calibrated, so you can use the period of the star's variation to find its absolute magnitude. Then by comparing its absolute and planet magnitudes, you can find its distance. So do you all recognize this space vehicle? Any suggestions, any ideas? everyone still hear me? So this is the Hubble Space Telescope. So if you are familiar with one of our normal public transport buses, such as those PATCO buses, the Hubble telescope is about the size of one of them. So even with the Hubble Space Telescope, Shepherds are not visible in galaxies much beyond 30 megaparsecs. So astronomers must search for less common but brighter distance indicators and calibrate them using nearby galaxies that contain both indicators. For example, by studying nearby galaxies with distances known from Shepherds, astronomers have found that the brightest globular clusters have absolute visual magnitudes of about -10. If you found globular clusters in more distant galaxy, you could assume that the brightest of the globular clusters have absolute magnitudes of -10 and use that information to calculate its distance. Astronomers calibrate type 1a supernovae, those produced by the collapse of a white dwarf, because the white dwarf always collapses at the same mass limit. So the explosions reach approximately the same maximum luminosity. When the type 1a supernovae occur in galaxies with distances that are known from Shepard variables and other distance indicators, astronomers can find the absolute magnitude of the supernovae at peak brightness. An example is shown in figure 13.4. When astronomers see a type 1a supernovae in a more distant galaxy, they observe the apparent magnitude of the supernovae at maximum and compare with the known absolute magnitude these supernovae reach at maximum to find the distance to the galaxy. So in this image, we can see in the image A, so the image on the left. So while dinosaurs roamed Earth, a white dwarf in a galaxy NGC 1309 collapsed and exploded as a type 1a supernova. And the light from that explosion reached Earth in 2002. Astronomers found Shepard variable stars in the galaxy, so they can determine that it's 120 million light years away. And that allowed them to find the absolute magnitude of the supernovae at its brightest. The supernova had faded from view 3 years later, so in the right image in 2005. Even though the second image was made using the Hubble Space Telescope, by comparing observations of many supernovae, astronomers have been able to calibrate type 1 supernovae as distance indicators. Notice how astronomers use calibration to build a distance scale reaching from the nearest galaxies to the most distant visible galaxies. Often astronomers refer to this as the distance pyramid or the distance ladder, because each step depends on the steps below it. The most dependable step is the Shepard variable stars. But notice that Shepard distance indicators depend on astronomers' understanding of the stellar luminosities and of the stars in an HR diagram. And that rests on an even lower step in the ladder, measurements of the parallax of stars. Stellar parallaxes in turn depend on measuring the size of Earth's orbit around the Sun, which finally rests on the bottom step, measuring the size of Earth itself. The distance ladder ultimately connects the size of the Earth to the most distant galaxies in the universe. The most distant visible galaxies are over 3,000 megaparsecs away. And at such a distance, you see an effect akin to time travel. When you look at a galaxy that is millions of light years away, you do not see it as it is now, but as it was millions of years ago, when its light began the journey towards Earth. So when you look at distant galaxy, you look back into the past by an amount called the look-back time. A time in years equal to the distance in light years the light from the galaxy traveled to reach Earth. This is quite an important aspect. Is everyone comfortable with the idea of look-back time? Okay, that is good to know. So the look-back time to nearby objects is usually not significant. For example, the look-back time across a football field is a tiny fraction of a second. The look-back time to the moon is 1.3 seconds. To the sun, only 8 minutes, and to the nearest star, a bit over 4 years. The Andromeda Galaxy has a look-back time of over 2 million years. But they are mere eye blink in the lifetime of a galaxy. So if you look at more distant galaxies, the look-back time becomes an appreciable part of the age of the universe. Although astronomers must work carefully to measure the distance to a galaxy, they often estimate such distance using a simple relationship that was first noticed about the same time the astronomers were beginning to understand the nature of galaxies. Early in the 20th century, astronomers were able to record the spectra of the brighter galaxies. And most have redshifts as if they were receding. The faintest galaxies had largest redshifts. In the 1920s, astronomers Edwin Hubble and Milton Emerson was able to measure the distances to a number of galaxies using Shepard variable stars. And in 1929, they published a graph that plotted the apparent velocity of recession versus distance for their galaxies. So here we can see this line. So Edwin Hubble and Milton Emerson first diagram of the apparent velocities of recession and distances of galaxies did not probe very deeply into space, and the horizontal axis was later recalibrated. And these data did show, however, that the galaxies are receding from one another. And this is actually quite an important discovery. Does anyone know what this discovery is, or where this is leading up to? Or let me rephrase it, what this gradient of this line represents? Almost. So this is called the Hubble constant and Hubble's law, and it describes how far or how fast the universe is expanding. So the simple relationship between apparent velocity of recession and distance is known as the Hubble law, and the slope of the line is the Hubble constant, and that's denoted by h. The Hubble law has important implications. It is commonly interpreted to show that the universe is expanding. The distance to a galaxy can be found by dividing its apparent velocity of recession by the Hubble constant. This makes it relatively easy to estimate the distances to galaxies because a large telescope can record the spectrum of the galaxy and determine its apparent velocity of recession even when it's too distant to have visible distance indicators. Edwin Hubble's original measurements of h were too large because of calibration errors, and in his distance measurements, so the most precise modern measurements of the Hubble constant h yield a value of 70 kilometers per second per megaparsec, with an uncertainty of just a few percent. So when we are talking about the universe is expanding, the universe is expanding at this rate, 70 kilometers per second per megaparsec. So once you find the distance to a galaxy from the distance indicators or the Hubble law, you can calculate its diameter and luminosity. With a good telescope and the right equipment, you could easily photograph a galaxy and measure its angular diameter in arc seconds. If you know the distance, you could use the small angle formula to find its linear diameter. And if you also measure the apparent magnitude of a galaxy, you could use the distances to find its absolute magnitude, and from that, its luminosity. The results of such observations show that galaxies differ dramatically in size and luminosity. Irregular galaxies tend to be small, so 5 to 25% the size of our galaxy, and of low luminosity. Although they are common, they are easy to overlook. Our Milky Way galaxy is a large and luminous compared with most spiral galaxies, though astronomers know of few spiral galaxies that are even larger and more luminous. The largest is nearly 5 times bigger in diameter and about 10 times more luminous than the Milky Way. Elliptical galaxies cover a wide range of diameters and luminosities. The largest, called giant ellipticals, are 10 times the diameter of our Milky Way. Many elliptical galaxies are very small dwarf ellipticals, only 1% the diameter of our galaxy. Of the 3 basic parameters that describe our galaxy, you have found 2, diameter and luminosity. The third, as was the case for stars, is more difficult to measure. So here is a reasoning of numbers again. So this is something I could ask in the exam. And that is basically the Hubble law. So the apparent velocity of recession of a galaxy is measured in VR, in kilometers per second, and is equal to the Hubble constant h multiplied times the distance to the galaxy d in megaparsecs. So here we have the velocity of recession equals the Hubble constant times distance. And astronomers use this way to estimate the distance to galaxy apparent velocity of recession. So if I give you an example and say, if a galaxy has a radial velocity of 700 kilometers per second, and the Hubble constant is 70 kilometers per second per megaparsec, and the distance to the galaxy equals the velocity divided by the Hubble constant, which is, so we take basically this equation, we solve for d, and then we can see it's 10 megaparsecs away. So that is quite easy. Is this a easy example? If I ask you something like this in the exam, will you be able to solve it? Awesome. So for a galaxy, the most difficult thing to determine is its mass. So although the mass of a galaxy is difficult to determine, it is an important quantity. It tells you how much matter the galaxy contains, which in turn provides clues to the galaxy's origin and evolution. Although there are few ways to estimate the mass of a galaxy, the most direct measurement uses Kepler's third law of planetary motion. In Chapter 8, Section 5, you used that law to find the masses of binary stars. If astronomers can measure the radius of a galaxy and the velocity with which it rotates, they can easily find the orbital periods of the stars as they orbit a galaxy. They then can use Newton's version of Kepler's third law to calculate the mass of the galaxy. The most accurate of these studies involve observing the rotation of the galaxy at different distances from its center and drawing a graph called the rotation curve of the galaxy. So in this image, we can see an image A. In the upper panel's artwork representation, an astronomer has placed the image of the galaxy over a narrow slit so that the light from the galaxy can enter the spectrograph and produce a spectrum. A very short segment of the spectrum shows an emission line redshifted on the receding side of the rotating galaxy and blue shifted on the approaching side. Converting these Doppler shifts into velocities relative to the galaxy's center, the astronomers can plot the galaxy's rotation curve on the right. Then in image B, real data are shown in the lower panels. Galaxy NGC 2998 is shown over the spectrograph slit, and the segment of the spectrum includes 3 emission lines. The most accurate of these studies involve observing the rotation of a galaxy at different distances from its center and drawing a graph called the rotation curve of the galaxy. Using such a graph to find the mass of the galaxy is called the rotation curve method. It is the most accurate way to find the mass, but it works only for nearer galaxies. whose rotation curves can be observed. More distant galaxies appear so small astronomers cannot measure the radial velocity at different points across the galaxy. Measuring the masses of galaxies reveals two things. Firstly, the range of masses is wide, from 1 million times smaller than a Milky Way galaxy to 50 times larger. And second, galaxies contain dark matter and spread through extended galactic coronae, just as our Milky Way galaxy. One last region remains to be explored: what lies at the center of galaxies. Our Milky Way galaxy contains a 4 million solar mass black hole at its center, and do all galaxies contain similar objects? And as we discussed in yesterday's class, yes, all galaxies contain a black hole. Rotation curves showed that the motions of the outer parts of a galaxy, but it also is possible to detect Doppler shifts of stars orbiting very close to the centers. Although these motions are not usually shown on rotation curves, they reveal something astonishing. Measurements showed that the stars near the centers of most galaxies are orbiting very rapidly. To hold stars in such small short period orbits, the centers of galaxies must contain millions or even billions of solar masses in a very small region. The evidence shows that the nuclei of many galaxies contain supermassive black holes. The Milky Way contains a supermassive black hole at the center, and evidently that is typical of galaxies. So we are all familiar with the image on the left, which is the first image of a black hole that was recorded by the Event Horizon Telescope. Such a supermassive black hole cannot be the remains of a dead star. That would amount to only a few solar masses. Rather, a supermassive black hole either formed as the galaxy formed or accumulated mass over billions of years as matter sank into the center of the galaxy. Measurements showed that the mass of a supermassive black hole is related to the mass of a central bulge. A galaxy with a large central bulge has a supermassive black hole whose mass is greater than the black hole in a galaxy with a small central bulge. Rare galaxies lacking central bulges usually also lack supermassive black holes. This suggests that a supermassive black holes formed long ago as the galaxies formed. Of course, matter has continued to drain into the black holes, but they do not appear to have grown dramatically since they formed. A billion solar mass black hole sounds like a lot of mass, but note it is only roughly 1% of the mass of a galaxy. The 4 million solar mass black hole at the center of the Milky Way galaxy contains only 1/1000% of the mass of our galaxy. And that brings us to dark matter, because where is the rest of the mass located in our galaxy? So given the size and luminosity of a galaxy, astronomers can make a rough guess as to the amount of matter it should contain. They know how much light stars produce, and they know about how much matter there is between the stars. So it is quite possible to estimate the mass of a galaxy from its luminosity. But a measured mass of a galaxy is generally 10 times larger than the estimated form of what is visible. This means that nearly all galaxies contain dark matter. X-ray observations reveal more evidence of dark matter. X-ray images of galaxy clusters shown that many of them are filled with very hot low-density gas. The amount of gas present is much too small to account for the dark matter. Rather, the gas is important because it is very hot and its rapidly moving atoms have not leaked away. Evidently, the gas is held in a cluster by a strong gravitational field. To have a high enough escape velocity to hold the gas, the cluster must contain much more matter than what astronomers can observe directly. The detectable galaxies in the Coma cluster, for instance, amount to only a small fraction of the total mass of the cluster. So here in this image, we can see the Coma cluster. And it's a cluster of galaxies containing at least 1,000 galaxies and especially rich in E and SO galaxies. So that means elliptical and lenticular galaxies. So S0 is, I forgot what F-gamification is. My mind is at 100 places. So two giant galaxies lie near its center. So only the central area of the cluster is shown in this image. If the cluster is visible to the unaided eye, it would span 8 times the diameter of the full moon. Then in image B, we can see in false colors X-ray image of the Coma cluster show it is filled and surrounded by hot gas. So note that the two brightest galaxies are individually visible in the X-ray image. So do you guys mean what is meant when we say they are false color? So yes, now S0 is lenticular galaxies. So what is meant by false color? Can everyone still hear me? So when it means a false color is, it means a false color, this is not the true color of X-rays, but we rather assign a color to it that we can interpret it ourselves and interpret it better. So another way to detect dark matter goes back to 1916, when Albert Einstein described gravity as a curvature of space-time. The presence of mass actually distorts space-time, and that is what you feel as gravity. He predicted that a light beam traveling through a gravitational field would be deflected by the curvature of space-time, much as a golf ball is deflected as it rolls over a curved putting green, and that would result in twice the deflection prediction by Newton's theory of gravitation. So the effects have been observed, and it's a strong confirmation that Einstein's theories are correct. So question, I don't understand the use of false color. Okay, so let's go back one slide. So when we look here at these images, so we call these two images false color images because those are not the actual colors we are perceiving by the telescope. So these, for example, let's take the X-ray one. We cannot see X-rays with our naked eye. But if we look at it, we can detect X-rays. So we, for example, in false color in this, we can assign a color to the radio image and we say purple is X-rays. And the more whiter it becomes, the stronger the X-ray source is. The more purplish bluish it becomes, the less weaker the X-ray source is. So we assign a color to make it easier for us to interpret the data. And that is what we call false color. Does that help? It is a pleasure. So with this is how we can represent space-time. So what means is, if you can think of this as the green in a golf course, and this is the golf ball, the more heavy it is, the more distortions it will have. And that brings us to gravitational lensing. Occurs when light from a distant object passes a nearby massive object and is deflected by the gravitational field. The gravitational field of the nearby object is actually a region of curved space-time that acts as a lens and deflects the passing light. Astronomers can use gravitational lensing to detect dark matter when light from very distant galaxies passes through a cluster of relatively nearby galaxies on its way to Earth and is deflected by the strong curvature. The distortion can produce multiple images of the distant galaxies and distort them into arcs. And the amount of distortion depends on the mass of clusters of galaxies. So what this means is here is Earth, here is a galaxy in the way. So in this case, it's a quasar, meaning it has an active nuclei. And here is a different galaxy in the far background. So with all the dust and gas of the galaxy, and let's take something to draw with, let's make yellow. We cannot see the light passing through this galaxy. We can see some radio frequencies, but not really. But due to the mass of this galaxy, the light is now being bent around it, and we call that a gravitational lens. So now from Earth, if we look towards this galaxy, we see the galaxy on the background over here, and we see it over here, the two images. And this is what we see over here and over here, and that is the gravitational lensing. Everybody happy with this explanation? Awesome. So we can also see gravitational lensing around big stars as well. So if you look at a star, you can see other stars behind its light being bent around it as well. We can do that with our own sun even, and see different stars behind our own sun. So let me try and explain gravitational lensing again. So when we look at a galaxy behind this galaxy, its light cannot penetrate through it, so we cannot see this galaxy from Earth. But because this galaxy has such a tremendous mass, it bends the light around it rather than going through it. So now looking from Earth, we see the same galaxy over here, and we see the same galaxy over there. And this is this image we are seeing here, this image we are seeing there. So the light is being bent around the galaxy, and therefore we can still see it. So therefore it proves that the larger mass we have, it can actually bend light around it, and we call that gravitational lensing. Does that help a little bit better? Awesome. Observations of gravitational lensing made with very large telescopes reveal that clusters of galaxies contain far more matter than what can be seen. That is, they contain large amounts of dark matter. This confirmation of the existence of dark matter is independent of Newton's laws and gives astronomers great confidence that dark matter is real. Theorists conclude that dark matter must be made up of some as yet undiscovered subatomic particles that do not interact with normal matter, with each other, or with light. So dark matter is detectable only through its gravitational field. So this is why it is one of the outstanding things in astronomy that we are still trying to understand. We can detect dark matter through its gravitational field and gravitational lensing effects, but there's no other way to detect it directly. So if we look at our galaxy, this is just an artist's representation. We believe that all galaxies are filled with these dark matter, and that is where most of the mass of galaxies are actually located. So dark matter is not an insignificant issue. Observations of galaxies and clusters of galaxies show that nearly 90% of the matter in the universe is dark matter. The universe you see, the kind of matter you and the stars are made of, has been compared to the foam of an invisible ocean. Dark matter remains one of the fundamental unresolved problems of modern astronomy. So in this image A here in the middle, we can see the gravitational lens effect is visible in galaxy clusters as its mass bends the light of a much more distant galaxy to produce arcs that are actually distorted images of the distant galaxy. This reveals that galaxy clusters must contain large amounts of dark matter. So when we look at this, these arcs we are seeing right here are the gravitational lensing effect. So these are here, again, gravitational lensing effect that we can see. In image B, so the one up here, we can see when two galaxy clusters passed through each other, normal matter in pink collided and was swept out of the clusters, but dark matter in purple detected by gravitational lensing was not affected, meaning that normal matter does not interact with dark matter. So now when we put again our classification schemes, you don't need to know all of these classifications, only the most 6 important ones that we've learned. We have elliptical 0, elliptical 3, elliptical 6, spiral 0, spiral A, spiral B, spiral C. We have a barred spiral, or spiral barred, spiral barred, spiral barred, spiral barred, and then irregular. So how do galaxies evolve and how do galaxies start? So considering the origin of our Milky Way galaxy, presumably other galaxies formed similarly. But why did some galaxies become spiral, some elliptical, and some irregular? And an important clue to that mystery lies in the clustering of galaxies. Single isolated galaxies are rare. Instead, most galaxies occur in clusters containing a few to a few thousand galaxies in volumes 1 to 10 megaparsecs across. Our Milky Way galaxy is a member of a small cluster, and surveys have catalogued thousands of other clusters. For purposes of this study, you can sort clusters of galaxies into rich clusters and poor clusters. Rich clusters contain 1,000 or more galaxies, and mostly elliptical, scattered through a volume of roughly 3 megaparsecs in diameter. Such a cluster is nearly always condensed. That is, the galaxies are more crowded near the cluster's center. At its centers, such clusters often contain one or more giant elliptical galaxies. The Virgo cluster is an example of a rich cluster. It contains more than 1,500 galaxies and is 16.5 megaparsecs, so 54 million light years from our own galaxy. The Virgo cluster, like most rich clusters, is centrally condensed and contains the giant elliptical galaxy M87 at its center. So when we look at this, this is what the Virgo cluster would look like. So Virgo, a laboratory for studying galaxy evolution. So here is the Virgo cluster and some of the clusters we can observe. And these different colors are again false colors, and we denote them to show how fast these galaxies are moving. Poor clusters contain fewer than 1,000 and only often a few galaxies spread through a region that can be as large as a rich cluster. That means the galaxies are more widely spread. Our Milky Way galaxy is a member of a poor cluster known by the unimaginative name the Local Group. So I know astronomers can sometimes think of the most boring and also the most exciting names for some of the objects we are observing. So in this image A on top, we can see the Local Group. And our galaxy is located off the center of this diagram. And the vertical line gives distances from the plane of the Milky Way and are solid above the plane and dashed below. Then image B, we can see the Sagittarius dwarf galaxy lies on the other side of our galaxy. And if you could see it in the sky, it would be 17 times larger than the full moon. And then in image C, We can see, as shown in this artist's rendering of a mathematical model, the Canis Major Dwarf Galaxy orbited our Milky Way galaxy a number of times, and tides have ripped the stars and gas away to form streamers. The total number of galaxies and the local group is uncertain. It probably contains about 40 galaxies scattered irregularly through a volume of roughly 1 megaparsec in diameter. Of the brighter galaxies, 15 are elliptical, 4 are spiral, and 13 are irregular. The total number of galaxies in a local group is uncertain because some galaxies lie in a plane of the Milky Way galaxy and are difficult to detect. For example, a small galaxy known as the Sagittarius Dwarf has been found on the far side of our own galaxy, where it's almost totally hidden behind the star clouds of Sagittarius. Even closer to the Milky Way galaxy is the Canis Major Dwarf Galaxy. This galaxy was found by mapping the distribution of red supergiants detected by the 2MASS infrared survey. There are certainly other small galaxies in our local group that have not been detected yet. In general, rich clusters tend to contain 80 to 90% of elliptical and spiral zero galaxies, and a few spiral. So S0 is lenticular galaxies. In other words, galaxies that are crowded together tend to be E or lenticular rather than spirals. Poor clusters contain a larger percentage of spiral. Among the rare isolated galaxies are not in clusters, over 80% are spirals. Somehow the environment around a galaxy helps determine its type, and astronomers suspect that collisions between galaxies are an important process. Galaxies should collide fairly often. The average separation between galaxies is only about 20 times their diameter, like two blindfolded elephants blundering about under a circus tent. Galaxies should bump into each other once in a while, and stars, on the other hand, almost never collide. In the region of the galaxy near the Sun, the average separation between stars is 10 to the power 7 times the diameter. Consequently, a collision between two stars inside a galaxy is less likely than a collision between two gnats fitting about a football stadium. So when we are looking at colliding galaxies, there are 4 important points and 3 new terms that we need to understand. The first one is interacting galaxies can distort each other with tides, producing tidal tails and shells of stars. They may even trigger the formation of spiral arms. Large galaxies can also absorb smaller galaxies and produce a process called galactic cannibalism. Secondly, interactions between galaxies can trigger rapid star formation. Thirdly, evidence left inside galaxies in the forms of multiple nuclei and conflicting directions of star and gas motions reveal that they have suffered past interactions and mergers. Fourthly, the beautiful ring galaxies are understood to be bullseyes left behind by high-speed collisions. So evidence of galaxy mergers is all around you. Our Milky Way galaxy is a cannibal galaxy snacking on the nearby Magellanic Clouds. Furthermore, our galaxy's tides are pulling the Sagittarius Dwarf Galaxy apart, and the Canis Major Dwarf Galaxy has been almost completely digested as tides have pulled stars to from great streamers wrapped around the Milky Way galaxy. So our galaxy has almost certainly dined on other small galaxies. The test of any scientific understanding is whether you can put all the evidence and theory together to tell the story and history of the object studied. Can you describe the origin and evolution of the galaxies? Just a few decades ago, it would have been impossible. But evidence from space telescopes and new generation telescopes on Earth, combined with advances in computer modeling and theory, allows astronomers to outline the story of galaxies. So before you begin, you should eliminate a few old ideas immediately. It is so easy to imagine galaxies normally evolve from one type to another that you can call that a common misconception. So galaxies do not evolve from one form to another. But an elliptical galaxy cannot become a spiral galaxy or an irregular galaxy because ellipticals contain almost no gas and dust from which to make new stars. That means elliptical galaxies can't be young galaxies. But you can also argue that spiral and irregular galaxies cannot evolve into elliptical galaxies because spiral and irregular galaxies contain old stars as well as young stars. The old stars tell you that spiral and irregular galaxies can't be young. The galaxy classes tell you something important, but a single galaxy does not change from one class to another any more than a cat can change into a dog. Another old idea was that each galaxy formed from a single cloud of gas that contracted and formed stars, which astronomers refer to as the top-down hypothesis. Abundant evidence now indicates that large galaxies such as the Milky Way do not form primarily by top-down contraction, but instead by bottom-up accumulation of smaller clouds of gas and stars, and an inflow of gas and the absorption of small galaxies. Elliptical especially appear to be the product of galaxy collisions and mergers. They are devoid of gas and dust because it was used up in the rapid star formation triggered by the interaction or blown away by the eruptions of supernovae. In fact, astronomers see many starburst galaxies that are very luminous in the infrared because a recent collision has triggered a burst of star formation that is heating the dust, which radiates the energy in the infrared. Some of these galaxies are 100 times more luminous than our Milky Way galaxy, but so deeply shrouded in dust that they are very dim at visible wavelengths. In this image, we can see rapid star formation. Image A is a starburst galaxy filled with clouds of young stars and supernovae. In image B, the dwarf irregular galaxy began a burst of star formation about 25 million years ago. And image C, at least some starbursts are triggered by interactions between galaxies. So the innermost of M64, known as the Black Eye galaxy, are filled with dust produced by rapid star formation, and radio observations show that the inner part of the galaxy rotates backward compared to the outer part of the galaxy, a product of a merger, where the counter-rotating parts of the galaxy collide, star formation is stimulated. Many starburst galaxies show evidence of tidal tails and are probably the result of the merger of 3 or more galaxies that triggered firestorms of star formation and generated tremendous clouds of dust. The Antennae galaxies contain over 50 billion solar masses of hydrogen gas and will become starburst galaxies as the ongoing merger continues to trigger rapid star formation. As these galaxies use up the last of their gas and dust, making stars, they will probably become normal elliptical galaxies or merge to form a single elliptical. In contrast, spiral galaxies evidently have never suffered major collisions. Their thin disks are delicate and would be destroyed by the tidal forces generated during a collision with a massive galaxy. Also, they retain plenty of gas and dust and continue making stars, so they have never experienced a major starburst triggered by a merger. Of course, spiral galaxies can safely cannibalize smaller galaxies with no ill effects. The small galaxies do not generate strong enough tides to disturb the disk of a full-sized galaxy. We have seen plenty of evidence of cannibalism in our own galaxy. And some astronomers suspect that much of the halo consists of the remains of cannibalized galaxies. Evidently, our Milky Way has not collided with a galaxy of size comparable to itself so far. However, other evidence indicates that our galaxy will merge with the approaching Andromeda galaxy in a few billion years. And the final result will probably be a large elliptical galaxy. Bart's spiral galaxies may also be the products of tidal intersections. Mathematical models show that bars are not stable and eventually dissipate. Tidal interactions with other galaxies may regenerate and sustain the bars, while other half of all spiral galaxies have bars, suggesting that these tidal interactions are common. Other processes can alter galaxies. The S0 or lenticular galaxies may have lost their gas and dust as they orbited through the gas in their respective clusters. A galaxy moving rapidly through the thin gas filling a cluster would encounter tremendous wind that could blow the galaxy's gas and dust away. In this way, a disk-shaped spiral galaxy could be reduced to an S0 galaxy. For example, X-ray observations showed that a Coma cluster contains thin hot gas between galaxies, and astronomers have located in a similar cluster galaxy in the act of plunging through such gas and being stripped of its gas and dust. Small galaxies may be produced in a number of ways. The dwarf ellipticals are too small to be produced by mergers, but it could be fragments of galaxies ripped free during interactions. Now, the small ellipticals may be the cause of larger galaxies that had their outer stars stripped away during encounters. In contrast, the irregular galaxies may be small fragments splashed from larger galaxies during collisions, but retaining enough gas and dust to continue forming stars. A good theory helps you to understand how nature works, and astronomers are beginning to understand the exciting and complexity story of the galaxies. It is already clear that galaxy evolution bears some resemblance to a pie throwing contest. With the contrast of the first large radio telescopes in the 1950s, astronomers discovered that some galaxies, dubbed radio galaxies, were bright at radio wavelengths. Later, when telescopes went into orbit, these galaxies were found to be emitting energy at other wavelengths as well, and they became known as active galaxies. And modern observations show that the energy comes from the nuclei of the galaxy, which are now known as active galactic nuclei, or AGNs. And only a few percent of galaxies are active, but activity makes them especially prominent. So here we can see the bottom below in this image is a visual wavelength of an active galaxy. But if we look in the radio, we can see there's a lot of radio emissions coming from the nuclei or the center of this galaxy. And that is why it is called an active galactic nuclei. So when we look at our different galaxies, we can, or rather look at a galaxy, we look at it through different eyes. We can see different details from a galaxy. So here is visible light plus the Lassila telescope from the same galaxy. So this is infrared from the Spitzer telescope. This is millimeter wavelengths and submillimeter from ALMA. This is radio from the VLA. This is X-rays and radio and visible light, and this is X-ray from Chandra. So all of these images are from the exact same galaxy. And it shows if you observe the same galaxy in different wavelengths, what different information you can get from it. So this is also a good example of why we observe different objects in different wavelengths with different telescopes, so we can observe as much as the EM spectrum as possible to get as much information as possible. So everyone's still happy? Everyone's still following? Cool, thank you. So the first thing we are going to talk about leading up to active galactic nuclei and quasars are Seyfert galaxies. So in 1943, Mount Wilson astronomer Carl Seyfert published a study of spiral galaxies. Observing at visual wavelengths, Seyfert found that some spiral galaxies has a small, highly luminous nuclei with a peculiar spectra. And these galaxies are now known as Seyfert galaxies, and about 2% of spiral galaxies appear to be Seyfert galaxies. So Mount Wilson is also a very well-known optical telescope in the US, and it's still in operation today. So in this image, we can see in image A, this is NGC 1672. Seyfert galaxies are spiral galaxies with small, highly luminous nuclei, and some are interacting with nearby companions and appear distorted with tidal tails and bridges. So here in the top one, we have NGC 1672, and we can see its nucleus is bright. But in the center panel, we have NGC 1410, and that is connected by a long tidal bridge to its companions. So here we can see it's connected these two. And then in the last image, we can see NGC 7469 as a distorted companion at its lower left. So here is the distorted companion. What's with the naming of these galaxies? Are the letters and numbers random? No, it's not random. So when we look at different objects, there are a few naming schemes we can follow. So NGC is a acronym. Let me quickly check what it stands for. I can't remember now. Let me just quickly check. So NGC stands for the New General Catalog. So it's a new general catalog, and in that catalog, for example, the top panel, which is 1672, it is New General Catalog Object 1672. So there are different catalogs where certain classifications and certain objects are cataloged in. So there's a few catalogs in the last couple of 100 years, and the latest one we are working with is the NGC, so the New General Catalog. Does that help? Or explain it? Awesome. So you see, and also some of our examples we use. So for example, in one of our other galaxies, we showed M87. So M87 is called Messier Object 87, and it is named after the astronomer that discovered them, Messier. So therefore, it's in the Messier catalog. So the spectrum of a galaxy is the blended spectra of billions of stars, and consequently, weak spectral lines gets washed out. So galaxy spectra contain only a few of the strongest absorption lines found in stellar spectra. In contrast, spectra of Seyfert galaxy nuclei contain broad emission lines. Emission lines are produced by hot, low-density gas, so the gas and the nuclei of Seyfert galaxies must be highly excited. The width of the spectral line suggests that large Doppler shifts produced by high velocities in the nuclei. Gas approaching Earth produces blue-shifted spectral lines, and gas going away produces red-shifted lines. The combined light and gas approaching and receding therefore contains broad spectral lines showing that the velocities of the center of Seyfert galaxies are roughly 10,000 kilometers per second, about 30 times greater than velocities at the center of normal galaxies. So something violent is happening in the course of Seyfert galaxies. The brilliant nuclei of Seyfert galaxies fluctuate rapidly, especially at X-ray wavelengths. The Seyfert nucleus can change its X-ray brightness by a significant amount in only minutes. As you learned when you studied neutron stars, an object cannot change its brightness noticeably in a time shorter than the time it takes light to cross its diameter. The Seyfert nucleus can change in a few minutes, then it cannot be more than a few light minutes in diameter, about the size of Earth's orbit. In spite of their small size, the cores of Seyfert galaxies produce tremendous amounts of energy, and the brightest emit 100 times more energy than the entire Milky Way galaxy. Lots of energy is produced in a very small volume of extremely high temperatures and velocities. So what does this remind you of? Astronomers conclude that the centers of these galaxies contain supermassive black holes orbited by hot accretion disks, which matter is flowing into the black hole. Earlier in this chapter, you learned about evidence that most galaxies contain supermassive black holes at their centers. Nevertheless, most galaxies are not erupting. The shapes of Seyfert galaxies provide an important clue. About 25% of Seyfert galaxies have peculiar shapes suggesting that they have had tidal interactions with other galaxies. So in this image, we can see an image A, the Seyfert galaxy NGC 7674. It's part of a compact group of galaxies and is interacting with its smaller companions. So here we can see the galaxy, and here's a smaller one, and here is a smaller one. But in image B, looking at false color images in radio wavelengths added to this visual, we can see these two galaxies are interacting with one another, and the tidal tails extending to the left and upper right are more easily visible in this enhanced image, meaning these over here. So there's also statistical evidence that Seyfert galaxies are more common in interacting pairs of galaxies than in isolated galaxies. These clues hint that Seyfert galaxies may have been triggered into activity by collisions or interactions with companions. And you'll find more such evidence as you study other kinds of active galaxies. So, ladies and gentlemen, I think we will call it for today. So I will see you in class next week, Monday. Next week, Monday, I will also hand out your semester tests. So please make sure that you are in class to get your semester tests. Otherwise, have a wonderful evening and have a great week. So far, the averages are looking quite good, but I will give you all that information on Monday.